Hello everyone, it's my great honor to be here to introduce our work, CNN acceleration with joint optimization of practical PIM and GPU on embedded devices. My name is Tianyu WANG from the Chinese University of Hong Kong. This is the outline. I will first introduce the problem, background, and challenges, then comes to the overall architecture and technical details. Finally, I will give the experimental results. Nowadays, embedded AI emerges for more real-time and low-latency inference tasks, such as object detection. Although compared to the original GPU server, the embedded devices have lower energy consumption and are easy to be deployed in edge computing environments. They suffer from limited computation resources, which lowered their inference performance. Thus, people usually adopt lightweight CNN models to relieve the computation pressure in embedded devices. Different from the traditional convolution that has heavy computation, here we can see many large filters. The lightweight CNN models will use some techniques, for example, the depth-wise separable convolution provided by Google MobileNet to reduce the computation requirement. Unfortunately, with significantly reduced computation, here compared to VGG16, MobileNet has 30 times lower flops, but the memory data movements are not reduced as much as the computation. Here we can see only 12 times lower. Thus, the lightweight CNN models transfer the inference task from computation-intensive to memory-intensive, which makes the memory wall problem more severe. To break the memory wall, the processing memory technique has great potential. Here you can see that different from the traditional von Neumann architecture, that all the computation needs to be done at CPU or GPU side. The PIM architecture has some logic units inside DRAM to provide computation next to the data. In this way, the data movement between GPU and memory can be reduced to save the energy and accelerate some bandwidth-sensitive applications. However, due to the fabricating problem, many PIM-based CNN accelerators based on various memory platforms are hard to be widely deployed in embedded environments. Recently, Samsung fabricates a processing memory chip called HBM PIM, in which they replace half of the memory cells with some computing units called PCU to provide computation. Here we can see the orange background, they reduce the memory capacity that compared to the normal chip with the blue background, and add some PCU cores into it. But such simple PCU cores only have limited computation capabilities. Thus, we need the GPU PIM hybrid architecture to perform CNN inference tasks. To build the practical GPU PIM hybrid CNN accelerator, several challenges need to be addressed. Because PCU cores locate alongside memory cells, they have large bandwidth, usually 8 times higher than GPU. However, their simple logic determines that they cannot execute instructions as fast as GPU cores. Therefore, the first challenge is to schedule the lightweight CNN inference tasks between GPU-PCU cores to take both advantages of the GPU and PCU. First, we need to disaggregate one whole CNN inference task into some more fine-grained scheduling units. Then we can find an optimal offloading scheme to leverage the advantages of both GPU and PCU cores. Second, when multiple CNN inference tasks are running in parallel, we need to make full use of GPU and PIM resources while considering some practical limitations of PIM, such as the mode switches between the memory mode and the compute mode, and the memory address interleaving. Next, I will introduce the overall architecture of our solution and some technical details to address those challenges. Our solution includes a two-level scheduling policy for the first challenge and a PIM-aware memory layout optimization method for the second challenge. Specifically, at the inner level, we first propose a fine-grained roofline model to find an optimal CNN layer offloading scheme, then take it at the guideline to generate more offloading schemes. At the outer level, for multiple inference tasks allocation, we model it to a multi-dimensional knapsack problem and solve it by a dynamic programming algorithm. As for the memory layout optimization, we first analyze the intermediate results between CNN layers, Then propose several different data flows for data transmission from PIM to GPU, GPU to PIM, and PIM to PIM, respectively. Next, I will introduce our fine-grained roofline model. The roofline model is a widely used ideal performance analysis model. It takes the ideal floating point performance measured by flops per second and the ideal memory bandwidth in bytes per second to calculate an arithmetic intensity, AI, to indicate if a typical program is computation intensive or memory intensive. As the right figure shows, a typical hardware platform has its maximum flops and bandwidth, which can be illustrated as a horizon line and a roof line in the axis, respectively. Higher roof line indicates larger bandwidth, for example, as the HBM PIM's red line, while higher horizon line shows stronger computation capabilities, as the blue and green lines for NVIDIA Jetson NX. Instead of simply referring to a whole CNN model's arithmetic intensity, we analyze it layer by layer to find a more fine-grained AI value for each year. Therefore, we can get that depth-wise layers are memory-intensive with low AI values, while point-wise layers are computation-intensive with high AI values. According to that, we can clearly know which types of layer to be offloaded to which device that can have the most benefit. When we apply the fine-grained roofline model to our GPU PIM integrated platform, taking the Google's MobileNet as the example, we have different AI values for different layers, as the figure shows. Then we assign the layers with low AI value to be offloaded to PIM to gain benefit from its high memory bandwidth, while let the layers with high AI value to be executed still on GPU to get the maximum performance. Note that the first layer is reserved on GPU side because the whole image needs to be read out from memory at the beginning. If we execute the first layer on PIM, it will cause many inter-channel data movements due to the memory address interleaving, which harms the PIM performance. In the real world, we won't only perform one inference task at a time. It must be multiple inference tasks running in parallel. In that case, only the optimal layer offloading scheme is not enough, because it may not be able to exhaust the GPU and PCU cores simultaneously, wasting their resources. For example, all the layers in MomoNet will occupy 568 megaflops computation and 46.9 megabytes memory IOs. If only based on the optimal layer offloading scheme, we will have 550 megaflops computation and 29.1 megabytes I/O on GPU, and 18 megaflops computation and 17.8 megabytes on PIM. Taking the ideal maximum performance of Jetson NX and HBM PIM, when we exhaust GPU resources with as many inference tasks as possible, we only have very low PIM resource utilization. It shows a great GPU PIM load imbalance. To make full use of both GPU and the PCU cores, we propose an MDKP-based task allocation method. Firstly, we use a greedy-based algorithm to generate more offloading schemes by choosing one not yet offloaded point-wise convolution layer with minimum AI value to be offloaded to PIM. Now we have many different offloading schemes from GPU PIM balanced ones to PIM dominated ones. Then we need to answer this question. Each offloading scheme will be used by how many inference tasks? The answer is we can model it to a 4-dimensional knapsack problem and solve it by a dynamic programming algorithm. From the knapsack problem view, we have an infinite number of items because a layer offloading scheme can be chosen by many inference tasks, and our target is to put as many items as possible into the knapsack, which indicates that we can have as many inference tasks running in parallel as possible. Then I will introduce our second technique about the PIM-aware memory layout optimization. Because of the memory address interleaving technology that has been widely used in commercial DRAMs, a typical object that's larger than one memory cell size, 32 bytes, will be stored across multiple memory channels to exploit the channel-level parallelism. So, the original address interleaved manner to store the intermediate results is to spread them across multiple channels. Although in this way, the GPU can read results from all memory channels simultaneously to get maximum parallelism, when a typical PCU core needs those data, it must perform inter-channel memory access to retrieve data, which severely harms the performance. Therefore, we choose to store each image channel data inside only one memory channel for more convenient PCU data access. Without inter-channel data movement during PCU execution, we can eliminate unnecessary PIM mode switches and extra GPU loads. Accordingly, we propose different data flows for different intermediate results transmission between GPU and PCU cores. First, for the depth-wise convolution that executes on PCU cores, because it has the same number of input and output channels, we make each PCU calculates one image channel's convolution with a one-channel filter. Next, the intermediate results need to be transferred to GPU for point-wise convolution. At that time, the GPU will read all image channels' intermediate results out simultaneously and reorganize their memory layouts on the fly, then perform point-wise convolution. After that, each image channel's data will be transferred to one PCU core in an interleaved manner. Those are the flows for GPU to PIM and PIM to GPU data transmissions, respectively. When two continuous layers are both offloaded to PIM, we will let GPU get involved to first collect all image channels data, then dispatch those data to all PCU cores using HBM PIM's all-bank mode. In this mode, we can distribute the same data to all PCU cores simultaneously with only one store operation, which saves the GPU resource. After PCU cores finish point-wise convolution, each PCU core can simply select its own part of data to perform depth-wise convolution. Finally, I will give out the experimental results to show the effectiveness of our proposed techniques. First comes the evaluation of the inference performance. As the yellow bar in figure shows, the only roofline model-guided layer offloading scheme exhibits significant performance improvement in post-estimation and SSD MobileNet V1, because these two network structures all adopt the DWSC technique, which is perfectly suitable for our GPU PIM hybrid architecture. For the other CDN networks, our two-level inference task scheduling policy with both MDKP and roofline model assisted outperforms all the other designs, as the green bar shows, because the MDKP model helps us to exploit further potential of GPU and PCU cores, making the full utilization of both the GPU and PIM resources. The computation resource utilization comparison can explicitly show the effectiveness of the MDKP model. With only roofline model-guided layer of loading scheme, you can see that all the CAN networks exhaust the GPU computation resources, while the PCU cores are even idle for most of the time. With MTKP assisted task allocation method, we can also fully exploit the potential of PCU cores, then gain benefit from both of them to achieve higher inference performance. The memory bandwidth utilization also shows similar trends. With MDKP model assisted, we use more PIM bandwidth, thus relieves the GPU bandwidth pressure. Although the PIM bandwidth utilization improves only a few percentage points, considering that the PIM bandwidth is 8 times higher than the GPU bandwidth, a little more PIM bandwidth utilization can help to save a lot of GPU bandwidth resources. Therefore, we can achieve higher inference performance. Here comes to the conclusion of this paper. In this paper, we for the first time propose a two-level scheduling policy to accelerate lightweight CAN inference tasks for the GPU PIM hybrid architecture. Specifically, a fine-grained roofline model is introduced to guide the exploration of the optimal layer of loading scheme. and an MDKP model is proposed for the allocation of multiple CAN inference tasks to make full utilization of both GPU and PIM resources. We also, for the first time, consider some practical issues when adopting PIM technology for lightweight CAN acceleration. Different data flows are presented to optimize data movements between GPU and PIM, with the consideration of PIM mode switches and memory interleaving issues. That's all my presentation. Thanks. All questions are welcome.